Hello and welcome to your second MEDC case study. So the case study is the Eyjafjallajokull Iceland 2010 eruption. Apologies for pronunciation, I'm absolutely certain that is incorrect, but that's my best effort. Anyway, so we're going to look at the Iceland eruption. It's one eruption, whereas our previous MEDC eruption was Mount Etna, which was over a number of years and it's continuous. And there are some similarities between Etna, but there are also some quite major differences. Okay, so we're going to use it as our second MEDC case study, mainly because of the impacts it had. They were local and global, but also its management and responses. Okay, it was very well managed, but the impacts were quite devastating on a global basis. So, getting started. Iceland is an island of about 103,000 kilometres squared in size, which is about 40% of the size of the UK. It's in the North Atlantic Ocean, it's about 65 degrees north in latitude, just short of the Arctic Circle. It's considered to be an MEDC, or a high-income country, either term is fine, and it has the following demographic statistics which tell us that it's an MEDC. So it has a birth rate of 13 children born per every 1,000 per year, a death rate of 7 people dying per 1,000 per year. The life expectancy is 81.1 years. This is 19th in world rankings. Total population is only 315,000 people, and the GDP per capita is $39,900. Okay, so moving onwards, looking at the tectonic setting of Iceland, you can see from the diagram on the right-hand side that Iceland sits on the mid-Atlantic ridge, and this is the submerged mountain range that extends from below the southern tip of Africa northwards into the Arctic Ocean. In our lessons on the plate margins, we have covered what happens at a divergent or constructed plate margin in quite a lot of detail, so this is just a recap. So the Mid-Atlantic Ridge is formed at the junction of two tectonic plates, the North American plate, which is moving to the west, and the Eurasian plate, which is moving to the east. And this combination of the plates pulling apart is why we get the term divergent. The plates are moving at a speed of 2.5 centimetres per year, so that means over 1 million years the plates will move apart by 25 kilometres. As the plates move, that allows magma to rise up from the mantle below, and this adds to the seafloor. The type of magma is basaltic, and therefore it has temperature of 1,200 degrees centigrade. It's going to be very fluid, okay, so it's going to actually move. When it does actually make volcanoes on the landscape, it's going to make shield volcanoes. This makes the new seafloor, this magma that's extruding outwards. The spreading ridge also coincides with a rising plume of magma, which we call a hotspot. So you've got two processes. You've got the hotspot magma plume, and you've also got the plates moving apart and allowing that magma from the mantle to actually extrude upwards. The hotspot is the central below Grimsvotn, and that's beneath the main ice field of Eyjafjallajokull. Okay, this is how come one of the hazards we get with eruptions on Iceland are the Jökullaups, okay, the flooding from glacial melt. So what I'd like you to do on with this information is, number one, watch the video on YouTube, and the web address is there, but I've also put the posters on Modo and the VLE for you. And it's actually a video we watched before, so it's How the Earth is Made, Iceland, and we have watched it before, but it might just be a good recap on the processes that are happening. You might find there's some additional notes that you can make. Secondly, having looked at this information, I would then like you to draw a fully labelled diagram of the Mid-Atlantic constructive plate margin showing the formation of Iceland. Okay, don't forget to include the mantle plume as well. And then your last task, I would like you to explain in a paragraph how the action at the plate margin and the mantle plume have formed Iceland. So watch the video, draw a diagram, make sure it's fully labelled and annotated, and then in your own words, please explain how Iceland is actually forming from these two processes of divergence and the hotspot. So, the lava characteristics of Iceland. I've provided you here with a table just summarising the differences between magma type and the eruption temperatures, the gas content, viscosity and the silica content. So basaltic lavas, which are the main lava from Iceland, occur mid-oceanic plate spreadings and hotspots, e.g. Iceland. Temperatures, 1,100 degrees centigrade to 1,200 degrees centigrade. Low gas content. And viscosity is very runny, lava flows, wide plateaus. You might get some sloping shield volcanoes or some lava swarms where the magma is oozing its way up into the fissures. And silica content is low at 50%. Okay, so these are your fluid, runny, hot lavas that can flow for long distances. And these are typical of Iceland. The acidic lavas are ones that we're more familiar with our Mount Pinatubo case study and our Vada del Ru's case study. Okay, so just to summarise that, the lava erupted to Iceland is basic, low silica content, it's dominated by metals, which they have a high melting point, hence the temperature of 1200 degrees centigrade, at which it actually solidifies. The eruption lava is much hotter, cool less quickly on exposure to the Earth's atmosphere, therefore they can spread further distances, and that's why we get shallow-sided shield volcanoes. Okay, so please make sure that you have a section in your notes on the lava characteristics of Iceland. So getting on to some background information about the named volcano. Eyjafjallajokull is the name of the glacier that sits on top of the volcano, meaning island mountain glacier. The volcano is actually called Eyjafjallajokull. The ice cap partly covers a gently sloping stratovolcano, so it's composed of ash and lava from eruptive periods producing tephra and lava, and they've been separated by hundreds of years of dormancy. The reason it's a stratovolcano rather than a normal shield volcano is the fact that because of the ice, it actually allows, when the material is erupting, it turns it into this kind of real fine ash. So you do get these layers building up. So it has the shape of a shield volcano, but it has got layers of ash and lava as a result of the ice and the interaction. But I'll talk more about that later. The volcano itself rises to a height of 1,666 metres, and it has a small caldera at the top of 2.5 kilometres wide. And it's located on the eastern volcanic zone, which is forming part of the Mid-Atlantic Ridge. Okay, so this is the timeline of events and nature of the volcanic eruption. So similar to what we did with Mount Etna, Nevada da Ruz, we have a timeline of the activity, and then we've looked at the type of eruption, so the nature of the eruption. So the task that I want to do is, what follows on the next two slides is a timeline of events of the Icelandic eruption, within which the nature of the volcanic eruption is described. So I'd like you to make a copy of the timeline as a flow diagram. And then secondly, use the information from the tectonic setting slide, so a couple of slides previous to this, the lava characteristics slide, and this timeline to write a summary of the nature of this volcanic eruption. So when we did the Mount Etna example, you talked about type of plate margin, the type of volcano, the violence of eruption, and the materials that were ejected. So embedded within this timeline is all the information that you need about the nature of this volcanic eruption. And have a look back at the tectonic setting and the lava characteristics slide as well. Okay, so that's the two tasks. So I'm just going to talk you through the timeline. So December 2009, you had increased seismic activity indicated the volcano was becoming more active. So this was monitored, and they could see that there was more earthquakes happening. Then February 2010, ground deformation was detected. So there were bulges in the shape of the volcano, and there was some deflation, and this suggested that magma was moving towards the surface. And earthquake activity got more frequent and got more powerful. Then 20th of March 2010 to the 12th of April, this is when there was the first eruption happened. Okay, so this eruption had two main phases. Some people classify it as two eruptions. We're going to look at it as one eruption with two phases of eruption. So 20th of March to the 12th of April, magma rose to the surface and was emitted from a number of vents on the flanks of the volcano in the form of lava flows. This was an effusive type eruption from fissures. So basically the fissures on the side of the volcano, magma squeezed up through them and extruded out onto the surface as gentle lava flows. Just lava, nice and gentle, down the slopes. Then, on the 14th of April, the main eruption started, also known as the second phase. So this was a summit eruption, and it started on the 14th of April with sustained activity until 22nd of May 2010. Okay, so by summit eruption, it means that the crater at the top, that was where material was blasted out and ejected from. Okay, so at the start of this eruption, there was increased seismic activity, but unlike the March eruption, this second eruption occurred under the ice cap, so this increased its explosive power. Okay, so this is quite complicated, and this is why we get those layers of lava and why we get those layers of tephra. So the heat from the eruption melted the overlying ice, that rapidly vaporized and quickly chilled this molten lava, caused it to fragment into highly abrasive glass-like shards of ash. These were then carried up into the eruption plume. Okay, so it's all about that ice being on top and how it caused it to break into these tiny glass-like shards of ash. The ash was fine-grained, 24% of it was under 10 micrometers, so this is very tiny, same as an aerosol is. And then the explosive power of the eruption was sufficient to carry the ash 9 kilometres in the atmosphere, where it reached the troposphere, and then it moved east, severely affecting air traffic throughout Europe. Okay, so we're linking it here to your weather and climate knowledge about the troposphere. The melting of the ice-covered summit, caldera of Eyjafjallajokull, caused flooding, so jollogops, in the adjacent lowlands. So you've got a really bad potential hazard there. And the eruption was rated at level 4 on the volcanic explosivity index. So Mount Etna was level 3. Here we've got a level 4. So slight difference. And remember that volcanic explosive index is logarithmic. So 3 is 10 times greater than a 4 is 10 times greater than a 3 was. Sorry, I get mixed up there. So the eruption continued intermittently until 21st of May 2010. And then after that point, lava stopped flowing and then only steam was released. And in October 2010, 28th of October to be exact, the eruption was declared to have finished. Okay, so you've got that kind of a timeline of events within which you've got information about the nature of the eruption, the plate margin, the materials it rejected, and the explosivity of it. In Iceland, the statement in red here, explosive eruptions are more common than effusive, which we wouldn't expect, being that it's a constructed plate margin, but it's because the eruptions frequently occur in interglacial settings, so with that ice. So what you get is these free-tone magmatic explosive activity, so where the water rapidly vaporizes, chills that lava, causes it to fragment. That's the reason why they're so explosive in Iceland. If there was no ice there, it would be a gentle, effusive eruption, just like Mount Etna in Italy. What I'd like you to do now is to watch the video clip at www.discovertheworld.co.uk. I've put the link on the VLE Edmodo for you, whatever way you're accessing it. It's just a nice video to show you the different stages of the eruption and just to consolidate that timeline event. The image I've presented here for you is just showing the height at which the ash actually got to, and then how it was moved eastwards and kind of affected Europe. What I'd like you to do now is to pause this video and to go onto the VLE or Edmodo and to open up the PowerPoint of all the images of the eruption. There are some truly amazing pictures showing you the action of the volcano and the material that was ejected. You're welcome to print some of these out and add them to your file and annotate them to show the hazards, etc. But just take a moment to have a look at the amazing images. It really is spectacular geography. Okay, so starting to get on to the impacts and the management. You should have recently been introduced to this topic of exposure. So you would have done the volcanoes as a hazard lesson, in which we talk about vulnerability and exposure and factors that can influence a volcanic, the impact of volcanic eruptions. So with regards to exposure in the context of Iceland, it is one of the most volcanically active regions in the world. But it's got low population density and economic activity is pretty limited, so the exposure to the hazard is quite low. In mainland Europe, exposure is also relatively low, but it depends on the wind direction, and this determines the movement of the ash plume. Okay, so usually in mainland Europe, because of Iceland eruptions, we are not very exposed to it because the wind normally goes in our favour, doesn't bring the ejected material towards us. But during the 2010 eruption, there was a high-pressure system, or an anticyclone over the UK. You should have learned about this in Weather and Climate Miss Atkins. And this meant that the air was stable and very little wind. So all the material that was ejected, that ash plume, was blown east into Europe, and that's what happened to cause our air flights to be cancelled. If there had been wind, this would have broken up the ash cloud, and there wouldn't have been an issue, because the air in the anticyclone moves clockwise, and it sucked the air from the northwest straight from Iceland to us. Okay, so just think about exposure and why in this particular year, so 2010, why we are actually exposed to it, where previously we're not. Okay, so that's considered a physical factor as well, so a reason why it actually caused the chaos that it did. Okay, so getting on to the impacts now. On the next 4 slides of this presentation, there is a summary of the impacts of the Icelandic eruption. Currently, the information is organised into local impacts of the eruption, so impacts on Iceland itself, and global impacts, so Europe and the world. This is just one way of being synoptic. So what I'd like to do is to copy down the notes in these 2 categories, so local and global, but then you need to actually summarise the notes in the following ways as well. So direct and indirect, short-term and long-term, positive and negative, into speed, which is social, political, economic, environmental, and demographic, and then temporary and permanent impacts. You can do this by making a table or a series of tables, or you can use some kind of colour coding system or a key. Your choice, but when we look in your folders for notes on impacts for Iceland, I'm expecting, and Miss Johnson will be expecting, to find that you have got the impacts categorised into all these different ways. Okay, so just trying to get you to think synoptically as you're taking down the notes. Okay, so the next couple of slides will give you all the notes you need. Do not do any more research in this. It's exactly what you need to do well. Okay, so first we're going to start on with local impacts. So this is impacts on the eruption of Iceland. So number one, we had flooding. So heat from the eruption melted ice under the ice cap. That meltwater was released and that caused flooding. Local floods beside the Markarfljót River were washed away, and bridges, farming, land and buildings were damaged. Overall, about 800 people had to be evacuated from their homes. Number two is disruption to farming. So farmers had to move their livestock indoors to prevent them from eating the grass or drinking water, which had been poisoned by the fluorine-tainted ash. Grass that had newly grown was suffered and just wiped out totally. However, in the longer term, the nutrients from the ash as it weathers away will improve soil fertility. So farming will have a positive knock-on effect in the future. The third point to make is airport closure. So the ash cloud closed Iceland's airspace, so there was a large temporary drop in the number of visitors, which hit tourism. This was very short-lived, and tourist organisations quickly exploited the situation by offering helicopter, bus and jeep tours to view the eruption. It was considered safe enough to actually go and watch the lava erupting from the volcano, and so people jumped on it. And so tourists, geographers, they all wanted to go see it for themselves, and so they took advantage, okay? By the end of March, 10,000 people had visited the eruption. And then as a result of that, you get the multiplier effect, so other attractions benefited too. So the glacial lagoon at Jökulsárlón had more visitors because there was just more people there. Number four, decline in air quality. So the heavy ashfall caused schools in Iceland to close. People had minor health problems, such as eye irritations, dry throats. However, the effects were actually quite short-lived. Moving onwards, we're going to look at the wider impacts of the eruption, and this all comes back to the closure of European air traffic. Okay, so every impact I'm going to talk about then links back to this main one. So the explosive force of the eruption carried the ash up into the path of the jet stream, which is a band of very fast, high-altitude winds. It was stable at the time, and the winds carried the ash in a southeasterly direction towards mainland Europe, and Europe is one of the busiest airspaces in the world. Okay, so it carried all that ash into the busiest airspaces. Civil aviation authorities chose to close the airspace because of concerns that the highly abrasive volcanic ash would damage aircraft engines, perhaps causing engine failure. And that comes back from the type of eruption, the fact it happened under the ice, rapid vaporization, and chilled the molten lava quickly, turning it into those glass-like shards. So they were really wary of how that would affect the engine, so they took no risks, they shut airspace, weren't allowed to fly in it. The volcanic ash could have also sandblasted the windscreens, reducing visual navigation, which could have then caused implications as well. Over 20 countries closed their airspaces at some point, and the flight ban even extended to East Russia and south to Spain. So airspace was closed over much of northern Europe for 6 days in mid-April, and then until mid-May, it was intermittent. So we had some open, some not. Okay, so there are quite a variety of positive and negative impacts associated with this, and this is what I'm going to lead on to now. So you've got the main air traffic being shut, closure of the European air traffic, and then the knock-on effects are as follows. So, firstly, losses in productivity. 7 million passengers worldwide were stranded due to airport closures. So they weren't able to get home, they were stranded in the country that they had gone on holiday to or on business in. So many of these people were on holiday and unable to return to work, which left businesses without employees. One estimate put productivity losses at 400 million a day. Okay, so if you think back to that, there were quite a number of teachers. I'm not sure, you might remember Miss Griffiths. She used to teach in geography. She got stranded when she was in Thailand on holiday, and she came home 5 days late. And there were quite a few teachers. And what our school did, was very nice of them, they actually paid the staff, even though they weren't in school for teaching because they couldn't get back, they gave them 1 week's worth of wages. Knowing that they couldn't get back because obviously it was the end of the month, people had been on holiday, spent all their money, and so they were obviously had issues. So our school did that, and other businesses have done a similar thing to help their employees because it was unexpected. They weren't expecting this to happen. Number two, air freight losses. So most goods are transported by road, rail and sea because of the high cost of air transport. Therefore, air freight losses were pretty much unaffected. But products such as pharmaceuticals or just-in-time deliveries of electronics and flowers did suffer because they rely on air transport. So flowers destined for European markets and worth 1.3 million rotted in warehouses in Kenya. So Kenya really lost, and also they sell a lot of their products like tomatoes, etc. in our markets, and again that comes by air. So they did actually really suffer, and people lost local jobs, etc. in Kenya. Tourism. The airline industry suffered huge losses, so 1.2 billion worldwide over 6 days. The airlines had no passenger revenue and also had to then cover the cost of rerouting planes and paying for the care of stranded passengers, so putting up in hotels and other accommodation options that they could provide. So it's estimated that it cost the airlines overall $200 million a day, and that 2 billion was lost overall from the whole situation. Companies who offered alternative transport to passengers, such as rail companies, e.g. Eurostar, cross-channel ferries, they actually gained from the disruption. People wanted to get home, they needed to get home, so they looked for alternative ways. So car rental firms, taxis and bus companies also gained too. Also, tourist destinations that had stranded passengers in them, unable to get home, benefited as people had to stay there longer. They spent more money on accommodation, on meals, family with young children, keeping them active, buying them stuff to keep them active, going to different rides, shows, etc. That all had a multiplier effect. Okay, so that benefited the tourist destinations because they had more tourist income in the destination where people were stranded. The decline in aircraft air and noise pollution was also another impact. The flight ban reduced carbon dioxide emissions over Europe, although there was some carbon dioxide released from the volcanic eruption. Aircraft noise near to airports was drastically reduced, so you've got some environmental impacts there, so positive environmental impacts. And then less fuel was needed because there was less airplanes in the air. 1.87 million barrels of fuel were not needed due to the cancelled flights, so the oil industry therefore lost money. Okay, so that concludes the impacts. You've got local and global. Having recorded these impacts in those two categories, go back to the slide where I talk about being synoptic in different ways, and then either do it as a table, colour code, or key, but you need to make sure that this information is presented in all those different ways to show your synopticity. Right, moving on to the last part of this case study, and that is the management of the eruption. So in lessons you would have been handed a document which tells you what information you need to know about each case study, and on that there's a volcano section and there's a volcano management and responses section. So it goes through about protection, prevention and prediction. And what I'd like you to do is to look through that and use the headings from this to record the notes that are presented on this slide on how the eruption of Iceland was managed. Okay, so what follows is a number of key points that I've picked out from all the literature that's available, and what you need to do is to categorise them into prediction, prevention or protection. So firstly, the eruption was monitored by the Icelandic Meteorological Office, or IMO. They work closely with the National Emergency Agency, the University of Iceland and the British Meteorological Office, and also the London Volcanic Ash Advisory Centre. Okay, so they all work together, so there was a good communication between all these different organisations to get the message across. Second thing is deformation was mapped with GPS geodesy equipment, so that GPS satellites were mapping the changes in the shape of the volcano. And INSAR techniques, so that's where radar images are used and they're kind of overlaid on top of each other to show how the land is changing over time. Okay, so try and make sure that you use that named equipment when you're talking about how it was monitored, the deformation, the change in the shape of the volcano was mapped. The height of the eruption plume was monitored throughout the eruption by using the weather radar at the Keflavik airport. Also, web cameras and visual elevations from ground and overview flights, so like helicopters were made too. And this was helpful in calculating the distribution of the ash. Okay, so working out how much ash there was and what direction it was all going to. And also it was the first eruption to ever be monitored with web cameras. So it was providing real-time information on the activity of the plume, and then that information was then given to people or the general population really easily. So they were getting text messages telling what was happening. The event was therefore tracked and prepared for, and the ash cloud was tracked by satellite by many different nations. So it was an eruption where everyone knew what was going on, and because it had such great significance. In Iceland, they set up a national crisis coordination centre, which was operated by the police, and they were responsible for communicating with the public, local, national and international authorities, the scientists and the media. Okay, so one way of controlling the panic was to make sure that you had one central organisation transferring the information to people in good time and making sure that the information was correct and accurate before a panic was instilled. Also, this centre was the hub for emergency operations. Okay, so everything was organised very effectively and therefore dealt with appropriately. There were also good response plans in place at the local level because prior to the eruption, they knew they were on a tectonically active area. Okay, everyone knows that Iceland is tectonically active. Okay, so they had trained their population in the local area what to do in case of emergency. Therefore, they had response plans already, which they were able to follow, and there were no issues. And one of the things they did do is that the area surrounding the volcano was temporarily evacuated for short periods of time during times of uncertain development of the volcanic activity in Jokull. So surrounding people, so there's 800 people that were evacuated. At certain points they went back to their homes when the hazard seemed to pass, and then they were removed again. Okay, so people were willing to do that because they knew that they were acting on timely advice. So make sure that you've got these points written down into protection, prevention and prediction. Remember, we can't really prevent an eruption from happening. Okay, so you have two categories you're going to be focusing on: prediction and protection. Okay, this is the last section of this presentation, which is on response to the eruption. What I'd like to do is to listen to what I'm going to talk you through and then read it through and then just add a notes section of responses in your file. So European Red Cross mobilised volunteers, staff and other resources to help people almost immediately. They set up centres to provide psychosocial support, give guidance on insurance issues and then help organise accommodation for people who were stranded in different European countries. So people that couldn't get any help through their airline, there was a way of getting support, accommodation. The Icelandic Red Cross had 60 volunteers and staff, and they worked 24/7 following the second eruption. They provided food for the farming population that were living close to the glacier. They provided counselling, in particular for traumatised children, so children that had been taken out of their homes in the middle of the night and taken to these rescue centres because their house was in the pathway of the lava flow or could have been affected by the glacial meltwater. So they worked in close coordination with the authorities and they set up service centres in the affected areas. They provided advice for people and the livestock. They held a 24-hour emergency information hotline. And they also provided meals twice a day in Heimeland, as most people had not been able to stock up on food. Okay, so they provided meals, so there was no secondary effects of starvation like we have in other eruptions. Okay, food was provided for people were given safe environments to stay within. They translated a guide published by the International Volcanic Health Hazard Network into Icelandic that was swiftly printed and distributed into the affected area to inform them of the health hazard linked to volcanic ash. So whereas at Nevada del Ruiz, the government were very slow at getting any messages across, people didn't know what the hazards were. In the case of the Icelandic eruption, information was quickly transferred, people knew the hazards and therefore did not put themselves at risk. Okay, so make sure that you've got your own notes on responses to the eruption, taking the key points from here.